Good morning, everyone. Welcome to my talk on the history of C#. I'm Bart. I'm working at Microsoft in Redmond as a software engineer in SQL Cloud, actually where we do research and development kind of things around data access in the cloud, big data transformations, those kind of things. And I started with C# all the way back in 2000, before it was even called C#. I had the opportunity as a student to be one of the beta testers at that time of the .NET framework, including the C# programming language. And so I've been playing with the language ever since. So today, it's almost like 10 years since the first version of C# was released. It's in fact about 13 years since the design of C# actually started in late '98, in the holiday season actually, around Christmas time. And so I wanted to step back a little and take a look at the things we've done over the last 10 years. So let's go all the way back, first of all, to 2001, when we released the .NET Framework 1.0, and sort of sketch what the problems were that we were faced with and why we actually chose to create a new language runtime. So the state of affairs was that, well, for the programming story of applications on Windows, you didn't have that much choice other than using either Visual Basic or native code. And native code was perceived to be pretty hard. It's also the case that we saw an increasing amount of people writing web apps, and classic ASP had some of its limitations, so it would make sense to have some new framework around that. It's also the case that there was limited cross-language interoperability in the previous development story for the Windows platform. So you had things like the component object model, where you could basically have two components talk to each other in terms of interfaces, but you couldn't say like, I'd like to define some class in, say, Visual Basic, and somebody else wants to derive from that class in a different language. So that kind of interoperability didn't exist. So that's some of the things we actually went after. And then there was also the trend towards Java. Actually, Microsoft was doing a lot of stuff in the Java community. We actually had a virtual machine at some point. We had things called Windows Foundation classes, which is a way to do Win32 applications using Java on the Microsoft platform. And so, as you might know, there were some lawsuits, and they said, well, you shouldn't ship any Java platform anymore. So we said, well, then we do our own runtime, and we'll actually build this thing called the .NET Runtime, originally codenamed Lightning. So here are some of the desirable properties that we set forward as some of the key design principles of the .NET framework. So first of all, we wanted to reduce the clutter, meaning that, well, we already have this perfectly suitable technique, for example, for error handling. It's called exceptions, structured exception handling, which you have in Java and C++ and those kind of languages. Let's do that instead of doing H-result error-based, error code-based one error handling. Also, registration of components, the typical hell of, you have a DLL and you need to register it in the registry. Why can't you just copy the DLL file over to some folder and it just executes? So we solved that problem with the .NET framework as well. Now, there were also some new trends. So if object orientation is the way forward, then the runtime should actually support object orientation from the bottom up. And also, we need to be real, because, well, we have all those existing investments, not just us, but also third parties, in things like native code, C++ code, COM components. Well, we need to be able to interoperate with those very smoothly. So those were some of the key design decisions around building the .NET framework. So we came up with this thing called the Common Language Runtime, the CLR, which is basically a virtual execution system or a virtual machine to execute code. And so at the core of it, you have a lot of facilities, including garbage collection, automatic memory management. You have some static type system. You have things like a just-in-time compiler that's used to take those abstract instructions into a variety of platforms at the bottom. So you see that we can compile at runtime into x86, x64, and many other platforms, like, for example, on Windows Phone 7. Well, Windows Phone 7 runs on some other processor architectures, and going forward, we'll see even more architectures we can basically compile into those. Now, on top of that, we have this thing called IL, which is the bytecode, if you will, of the Common Language Runtime, also known as Common Intermediate Language, or some people say MSIL for Microsoft Intermediate Language, on which we have many languages. So C#, VB, F#, Managed C++, Iron Ruby, Iron Python, all those things actually compile into IL code. And right from the start of the .NET framework, we actually had 24 languages that compiled into IL code, including things like COBOL even. if you're interested in that, well, lots of people wanted to get rid of their mainframes and their old infrastructure, so it made a lot of sense to be able to port it into, a .NET runtime. So by doing CIL, that language was actually designed with cross-language interoperability in mind. So that was one of the basic design principles of IL code. It needs to be able to accommodate static languages, dynamic languages. It needs to accommodate different kinds of, levels of static typing, dynamic typing. It also needs to accommodate, say, functional languages, which need tail call instructions, for example, not to exhaust the stack when they're doing some recursive algorithm. So those things actually shaped the IL code. It's also the case that the entire runtime is standardized in ECMA standard 335, and so third parties are actually free to implement the .NET runtime on different platforms. And so today you see that with Mono. Mono actually runs, for example, on Android, runs on Mac OS and different operating systems as well. So you can basically see a cross-language, cross-platform story shaping up here. Now, one remaining question, of course, is, well, why did you decide to do a new language? So the language was actually originally called COOL, for C-style object-oriented language. C-style stands for curly braces, semicolons, those kind of things. And the type appears in front of the variable as opposed to in an opposite order, so that's why we call it C-style. But why did we actually do this? So, because one of the design principles was to have cross-language interoperability, we said, well, we better make sure it's the case that this IL code and the runtime can really support multiple languages. So we had this project called Project 7, which was about implementing 7 industrial languages and 7 academic languages on the .NET framework. So people did that and were very successful doing so, but if you're porting existing languages, you need to maintain compatibility. And you need to make some new decisions, like, for example, taking Visual Basic 6.0 into the .NET runtime would require to add things like classes and polymorphism and those kind of things, which classic Visual Basic didn't have. So there's a lot of stuff to be decided if you port an existing language. So we said, well, we need to be pragmatic because we need people here at Microsoft to implement the base class libraries, collection types, system diagnostics, the system.string class, all of that stuff needs to be implemented. We need to have a language here that really exposes all the functionality, or as much of the functionality as possible, of the underlying runtime in a meaningful manner. So we designed the C# language to be that language. And so with that, we end up with, some of the design teams of C# 1.0. So what are the things we basically wanted to do? The first thing is, by looking at some other platforms, we noticed that, well, if you want to be object-oriented, it totally makes sense that any value, a primitive value like an integer, a long, a double, a decimal, all those things really derive from system.object, because then you can write, polymorphic containers, like a list of objects can contain an int. And you don't have to go to, creating a new integer with capital I and then passing in 42. So we say we want to have a common type system where there is a single root in the inheritance called system.object. So that's one of the things we actually did. Secondly, people, when talking about components, always talk in terms of a number of facilities on components, including methods. But there are many more just than ordinary methods. For example, people talk about, I have a button and it has a property that it has a text. Well, why do you want to have a get and a set method as opposed to something that tooling can reason about? That when tooling looks at reflection info can say, well, there is a property, it's called age on a person, and it happens to have a get method and a set method with different visibility. So you wanted to have richer metadata constructs available to express those higher order kind of mechanisms, such as properties, events, and indexers, even though at the bottom of the runtime facilities, those all boil down to methods. We still want to have rich reflection information on top of that. And for example, by doing that, we also had custom attributes like the square bracket syntax, so that you, for example, could decorate a method as being a web service method. So we had some rich metadata facilities built into the framework, and that was very helpful. Now, we also want to go beyond some existing art. The fact that we take exceptions as the way to basically do error handling in the .NET framework doesn't mean that we need to port all the exception handling facilities that different platforms thought about. For example, certain platforms do checked exceptions, and we think checked exceptions are generally a bad idea. They're actually a good idea, but in practice it doesn't work out that well. For example, if you have a checked exception and you have some facility that says, I will throw an I/O exception, Lots of people say, I will do that later on. I will catch the exception properly and do the right thing. And in the meantime, they say, just make the method throws exception. And then you've just defeated the whole purpose. You've just gotten rid of all the safety that you thought that you had to begin with. Also, when you have different components that all throw different kinds of exceptions, when you bring two components together, your list of checked exceptions starts to blow up, and you need to do a lot of things yourself to basically accommodate for the different exception types. And if exceptions are really exceptional, well, catching them in the first place needs to be something that's very well thought out. So we said, well, let's not do checked exceptions, because in general, we see lots of people abusing that and basically not doing the feature any justice. Some other things have to do with picking other defaults than other platforms did. For example, when we talk about object-oriented programming, the ideal theory is that you have an object, it has a lot of methods on it, and somebody can inherit from the object and basically override any behavior whatsoever. That's ultimate democracy. You can basically take the object and adapt it as much as you want. However, for versioning, that's not always the good thing. Say that you say, I will build a base type version 1.0. A base type, say, person. And it has 20 methods on it, and they're all virtual. And then you ship that thing, and people say, well, let's just extend person by a student type and override 19 of the 20 methods. And you didn't anticipate, oh, they will override this method and that method and that method. And now you come with version 2 of your base type called person. And then you say, oh crap, I need to be compatible with everyone that potentially can override the existing behavior. If you make things non-virtual by default, you have to opt in explicitly to saying this thing is extensible at those very points in time. And so that's actually something that we believe helps a lot with big library designs. And finally, there are some other ones, but I sort of highlight the most important ones. It's also about being pragmatic and realistic. You could say, let's squeeze myself through the abstraction of object-oriented programming all the way through. Like, in order to start a new thread, the only thing I need is an object that has a run method on it. So if I have an iRunnable interface or whatever, then I have enough to actually express a way to basically start a new thread. Well, we say that's true. You can have single method, abstract, base types, and whatever. But why can't you just pass in a type-safe manner the name of a method to somebody else? Why can't you just take a method up and say, this is the method you need to run on a different thread? So we introduced this notion of delegates, which you could think of as function pointers, but with a lot of type safety on top of them. So you can pass methods around as well, and that helped a lot with designing things all the way in 2005, 2008 with regards to LINQ, where we do functional style programming. You want to pass methods around really easily. So let's do a little demo of what we actually had back in the day in 2001. One of the most important features was this cross-language compatibility. So the thing I have here is a piece of F# code. Now, F# was only created later on, but you could perfectly envision here using, say, for example, J++ or managed C++ as some language that existed in .NET 1.0. And the thing I'm doing here is I'm basically creating a list of persons. In F# you actually write that as person list, not list of person. That's just functional style. And what you do here is we basically create, a person and then some derived type student that I also pass in. Now, the way this works is that the person type is actually defined in Visual Basic. So in Visual Basic, I have a person type that has a name and an age with different properties and a constructor and all of that stuff. It also has an override to the toString method that exists on system.object, as you can see over here. Now, the toString method is implemented by the BCL, and in fact, you're already overriding here something that's defined on system.object, which actually is written in C#. So you already see cross-language here, where VB talks to the underlying base class library. Now, to create a student, I said, well, let's add a reference from a C# project to the VB project, and basically inherit a student type from the person type that was defined in Visual Basic, because I'm more familiar to define students in C#. So what I can do here is I can do a base call, with name and age. I will pass in the year or the grade or whatever you want to call it. And I will override the toString method from Visual Basic by calling the base method, that's the Visual Basic method, and then append, the grade actually to the resulting string. And so if I press F5 here, you really see that F# is talking to C#, to Visual Basic. They're all sort of, happy together. So let's just press F5, and you see I'm hitting a breakpoint now on the toString method in the VB library, and that's basically because my F# code, and you see the debugger actually knows about the whole call stack across languages. I'm trying to print at this point, variable p, which will be the first element of the list, which is a person, which was defined in Visual Basic. So that's the reason I actually end up here in Visual Basic. If I press F5 again, we're trying to print the next person. The next person is a student. Students are defined in a C# library, and the C# library has an override to toString, which calls the base method that actually exists in Visual Basic. So you see all those things now blend together very nicely, based on object hierarchies and whatnot. So that was one of the strengths, of creating the common language runtime at that time, and that's the output of the program, as you can see over here. So far for .NET 1.0, just emphasizing the cross-language aspect of the runtime. Let's now take a look at what we did in C# 2.0. And C# 2.0 was really one of those releases where we catch up with the things that we wanted to do in 1.0, but one of the most important features of building software is shipping the software at some point. So if in 2001 you say, well, it's going to take another 4 years for us to do generics, or you might say, well, we can ship what we have now and do generics as the very first thing for the next release. Maybe the second thing is more appealing than the first thing, because then you're slipping 4 years. So we said, well, in C# 2.0, first thing on the agenda will be to support generics. Now, we have some other things here. I will talk about 3 or 4 of them. I also want to emphasize the backwards compatibility aspect. C# historically has always been backwards compatible from the language point of view with previous versions of the language. So if you take C# 1.0, a piece of code, and you actually compile it using C# 2.0, 3.0, 4.0, 5.0, and whatever, it should still work exactly the same as it did before. Which means that if we introduce new keywords, we need to introduce the new keywords as contextual keywords. So say that we have a new keyword called banana in .NET 6.0, then we should not clash with a variable that's called banana. And we do that by making the parser such that it only recognizes keywords in a certain context. So compatibility is a very big goal. And in fact, we already introduced some other keywords here in 2.0 that needed to be subject to this compatibility. So let's introduce generic types. So this is a piece of code from C# 1.0. It's the array list type, which is defined in system.collections. It inherits from, or it implements the IEnumerable interface, and I've just put 2 members here, an add method and a getEnumerator method to implement IEnumerable. So what I have here really is a multi-purpose collection type that can store any piece of data, including primitive types. Because we have a common type system, you can use the array list to populate it with integers without first lifting them into some special integer wrapper type. So this is the enumerator. If you look at the enumerator, the way you actually get data out of this collection, you can already see it's weakly typed. Everything goes to system.object because we want to store everything that possibly can be in the collection. Which will, of course, mean that in order to get data out of the collection, you will need to do things like casts. There are 2 things going on here, really. I have an array list, and I'm adding 42 to it, and hello. Adding 42 to the array list actually causes an allocation of an object on the heap that contains 42. That's because, the way the type system is designed. Now, boxing is one of the essential features of the common type system, but it also can be a little of a performance hit because things happen implicitly. So you want to get rid of that, especially for collection types, because then you might just have a collection with 10,000 numbers. You don't want to have 10,000 additional heap allocations that are subject to garbage collection for all those 10,000 elements. So boxing is something that comes in handy in a lot of cases, but when you have the big volumes of data, you don't want that to happen. Secondly, you need to have hidden casts, hidden or not hidden casts. First of all, there I try to extract the first element out of the list, which will be 42, and I need to cast it back to an int, which will do something called unboxing, to basically get a hold of value 42. However, in the second thing, in C# 1.0 we said, well, for each loops need to work on collections, and even though collections are still weakly typed in .NET 1.0, we actually made the syntax for the for each loop support implicit casting to the values inside the collection. So you can write something like for each int x in list without having to write object and then cast yourself. That was a conscious decision to make consuming collections friction-free. And that's actually a good thing because 99% of collections are heterogeneous anyway. They contain objects of the same type. In fact, I would say that this piece of code is a bug, having a list that contains both 42 and a string, which is totally unrelated. So in this case, actually, this piece of code will blow up the second iteration of the loop because we try to cast hello to an int. So with generic types, we want to do much better. So what's the existing art back in 2005 to do generics? Or better static typing? So the first approach would be to have something much like C++ templates. What C++ templates really are is compile-time polymorphism. What that means is that it's basically some rocket science macro expansion, nothing more, nothing less. You take your template, it has some holes drilled into it, and then when you instantiate the template with, say, for example, list of or vector of string, it will just compile a new type at compile time that's specialized to store strings. It's just substituting that T with string everywhere it sees that. That's very high performance, very powerful. You don't have things like runtime facilities to inspect, hey, this is a vector, but is the vector really a vector that contains strings or something else? Because all the information of the fact it was a template to begin with doesn't survive till runtime. So that's one of the things that we could consider a drawback of C++ templates. Another approach would be generics as they have been done in Java. So in Java, they chose the following approach. They said, well, we will do something called compile time type erasure. That means an array list of T is just syntactical sugar during compile time for an array list of objects, which is the base type, like just array list without the of T part. And at compile time, we'll do all the transformations to store your objects into that array list. Still, it doesn't work with primitive types because we don't have automatic boxing, those kind of things. And there are some issues, as I said, with primitive types. Like an array list of int, does it work, doesn't it work? Depends, I don't know what the ultimate solution was there, but it feels a little clunky on the edges. Now, the reason that they did that, and that's very understandable, is they said, well, we shouldn't change the runtime. We just want to have an array list of T be compatible with the non-generic array list that we had before. And that's, a conscious design decision, I guess, but we said, well, I think this is something we should do at the runtime level, because there are lots of benefits. So the thing we did is build generic collections by extending the runtime slightly and actually having deep support for them inside the CLR. So now you can define list of T, which implements IEnumerable of T and has that T appear in every position where you can have a type appear in regular syntax. The enumerator now becomes strongly typed. And in fact, now you get compile time checking that you can't add hello to a list of integers. And you don't have any cast, you don't have even boxing, because what really happens is that list of T will have some array of type T inside of it. At runtime, the CLR says, well, you're trying to instantiate a list of int. I'm going to create a special type for you at runtime, preserving all the metadata information so that I still know it's a list of T, but a special one. But I will create an optimized type layout for something that can store ints. And if then you try to do the same with persons, you will get a different layout optimized for your particular case at runtime. So generics actually came from a research project at Microsoft Cambridge in the UK called Gyro, which was actually done by people like Don Simon and Andrew Kennedy, who later actually created F# as the programming language. It's based on some type system. If you want to look at more details from a theoretical angle, you should search for System F or Système F because it comes from French community. It's done at the runtime level, which is really a little bit like C++ templates, but done in the JIT compiler. That's something you could think of, but it's more preserving rich reflection info than anything else would actually do. And it was actually supported immediately by C#, Visual Basic, and a lot of other .NET languages. So there are some more features we did in C# 2.0. Let's briefly cover those. Even though we had a common type system, we didn't have a common way to express nullability. So say, for example, that you have a price that's stored in a database of type decimal. Well, you couldn't really assign null to that thing. If you do an object relational mapper, you couldn't say, and the price needs to be null. So we introduced this thing called nullable types for value types, where you can now put a question mark with clean syntax, clean closure syntax. You can actually say int question mark, meaning that this is something that has 0 or 1 value. 0 value meaning it can have null, 1 value meaning it can have anything of type int, or decimal in this case. It's actually also based on generics because, well, as you can see, the int question mark syntax at the top would actually translate by the compiler into nullable of int, which is a generic type. So that's something that happens at that level. Then we have a feature that I would say one of those features that we didn't want to do in 1.0, we didn't think of that, and that we had a chance to do in 2.0 anyway. So generics was the biggest thing up the plate together with nullable types, but iterators were something where we actually went way beyond what we regularly would do. So we said, let's introduce this thing called iterators, which is a way to new up collections or sequences of data by building, a little piece of code that just does something called yield return. And it basically lazily evaluates that entire piece of code. So what's going on here? If you look at this code, I have something called getPrimes. That seems to be an infinite loop. It goes from 2 to infinity. In fact, it will overflow with an overflow exception if I go too far, because I used the checked keyword here to do checked arithmetic. But in essence, this thing is an infinite loop. Yet when I call getPrimes, this thing doesn't blow up with, I'm going forever. It's not making your program get stuck. The reason is that it returns an IEnumerable of int, which is a sequence on which you can do move next, move next, move next using a for each loop. And inside the body of the code, I'm using yield return of n. So what happens with this thing is that when I do something like for each int x in getPrimes, console write line x, and if n++ equals 10, so after the 10th iteration I want to break, that code is only going to execute 10 times at the top. So the getPrimes method, basically for the first iteration, it runs all the way till it finds a yield return, and then it pauses the execution of that method, gives you the value back, and then only when you say, please move to the next element, it starts executing again all the way to the next yield return, or a yield break to exit the method. So that's what's called an iterator. It allows lazy evaluation of computations of sequences. So you can basically create a method called give me all the natural numbers. That goes from really 0 to infinity. You just write an infinite while true loop, and it's just running as much as it needs to for the consumer actually to be satisfied. So if the consumer says after 10 iterations I break, so be it. It will not do any more work than those 10 iterations. In fact, on this particular feature, we based the design of language integrated query in .NET 3.0 or .NET 3.5 with C# 3.0. So let's take a look at that in just a moment, but first take a look at generics and iterators. So here I have a program that uses something called an iterator for a lottery. So basically I have a lottery method sitting over here that news up a random number generator in system namespace, and then has an infinite loop that basically sleeps for half a second to 5 seconds to keep up the suspense of picking the next ball out of the big jar. And then ultimately it returns a random number between 1 inclusive and 43 exclusive. So that's really the Belgian lottery, unless the thing has changed since I fled the country. So if I execute this thing now, let's say I set a breakpoint, well actually let's just press F10 and just step through the code a little bit. Once I start enumerating the results of the lottery, you will actually see when I do F11 here, that I end up in the lottery, and the lottery is running all the way till the first yield return. I'm doing a sleep right now, which could take up to 5 seconds. Well, it was one of the longer sleeps, apparently. And when I get out of here, I got a ball that actually comes from the lottery, which is value 38. You see, I actually quit that iterator code right at the point of the yield return. This thing didn't continue to execute. I just got the first value that I'm interested in, I have yielded it out, and I can actually put it on the screen. Next, I'm going to ask the user whether he wants to pick the next one, yes or no. So say that I'm that little cute lady there that says, yes, pull the next ball out of the jar. So I say yes, there we go. There we get value 34 coming out. Then I will do yes again, and then again, the iterator is moving till the next yield return, and out comes 13, and so on and so on. So that's really what's going on here, is that I do a console read key, and when you don't say no, we don't break from the loop, which means the iterator goes to the next stage. So it's totally lazily evaluated code. So that's actually something where we use both generics, because I use IEnumerable of int, as well as iterators with the yield return keyword over here. So based on that, we actually built something called Language Integrated Query, which we introduced in 2005 at the PDC in Los Angeles, I believe. And later in 2008, we actually shipped this thing. And the idea is that when you look at a lot of code, lots of people do querying, whether it's a relational database, an XML document, whether it's in-memory data. You want to write queries, like from this collection of data, which might live on some spindle in some data center, I want to get, the people that actually have an age over 18. And why do I have to learn 15 different languages depending on where the data lives? Do I want to learn XQuery if it's in an XML document, T-SQL when it's in a SQL database? Do I want to know some web service specification for Amazon data to query it in yet a different way? The answer is no. We can integrate query syntax inside the language and actually target all those domains using the same facilities. So that's the thing we actually did. We introduced something called query comprehensions in the .NET languages, C# and VB. So here you see a query over products, where I filter out the products with a price larger than $49.95. I order them descending by price, and then I select out some name and price. And finally, I can iterate over that, or I can data bind that to some UI. Now, the way this actually works is that the compiler does a translation of this piece of code into the following piece of code that's based on method calls as well as Lambda expressions. So what you see here is that the top-level code gets turned into a chain of method calls, some fluent interface kind of design, where we pass in Lambda expressions that actually are little pieces of code that will be evaluated, in this case for every element, to evaluate whether the element actually passes the check. We also have this invention called anonymous types, which is very useful to do projections, because in a lot of cases you want to say, I have a database, it contains 15 columns, but I only want to get 2 things out of it. Well, in order to use link, do you rather want to go to a separate file, new up a new type that has 2 properties, a constructor, a toString, and equals, and a get hash code? Or do you want us to create that type for you by just saying new type that contains a name and a price? And we synthesize the whole implementation of the object for you. So that's what anonymous types are for, especially used for select keywords. Now, in conjunction with anonymous types, we need something to refer to the type of something that doesn't have a name, because it's anonymous. So we introduced this thing called local variable type inference, the var keyword, which actually allows us to infer the type from the context. So for example, you can write something like var x equals 42, and we will know that 42 is an int 32, hence the var will actually be inferred to be an int. So using the var keyword, you can really abbreviate your code a lot, because say, for example, you want to new up some generic collection, dictionary of int to list of string, and you want to new that thing up. Well, what do you type today? You type something like dictionary of int to list of string x equals new dictionary of string from list and int and all of that stuff. Exactly the same thing. So now you can basically get rid of that type name on the left-hand side because, well, the compiler already knows the entire type name. And especially for anonymous types, well, you can't even say the type, because it doesn't have a name, so you need to use the var keyword in that case. Now, the var keyword is still totally statically typed. It's at compile time, the compiler knows what the type is. We don't do dynamic typing using the var keyword. So what can we do with link? Assume that products is actually something that's in memory, like a collection, like a list of product. I can basically query it using the link syntax on the previous slide, or just by using the method call syntax. And it so happens that we will find the where method on IEnumerable of t, because we implemented an in-memory version of link, of query operators, based on extension methods on top of IEnumerable of t. Extension methods is another feature that was added in C# 3.0. Actually, that allows you to take any type, including sealed types, non-virtual types, types like interfaces, and basically say, I want to add a method to it that looks like an instance method, that you can call like an instance method, but really is a static method that operates on the type from the outside. You don't want to sort of break into an existing type by sort of violating, sealed interfaces and whatever. So that's actually what extension methods do, and that's actually done using the this keyword on a static method's first parameter. And so inside this thing, that's the way we implement the where method, for example. The where method simply says, iterate over the entire source. I'm using the var keyword here, but I could also use for each tx in x's. I invoke the filter, which is a lambda expression, which is just a little piece of code that can get invoked because it's a delegate. So I can just call into that. If the filter returns true, I'm yielding out the result. Otherwise, I go into the next iteration. If the next one returns false, I will just continue going. So if the user says, I just want to get the top 5 products with the highest price, we will only get the first 5 products, and we will not even evaluate the filter for all the next products. That's because the whole thing is lazily evaluated, which is a very powerful technique. You can even deal with infinite collections because of that. So here's another case, and actually not much has changed between the 2 slides. Assume now that you wrote exactly the same query, but now against some different type, not a list of product, but say, for example, a table of product, where table of product is some object relational mapping technology for, say, for example, SQL Server. You can write exactly the same query, but the thing that happens now is that we find an extension method on something called iQueryable. And the only difference in the signature, other than the iQueryable instead of the iEnumerable, is what you see on the second line of my signature of the where method. Instead of passing in a func of t to bool, we pass in an expression of a func from t to bool. What that does, it's one of the biggest features of the C# compiler in terms of code size. It's one of the things that's the most underestimated. Basically what it does is when you assign a lambda expression to that parameter, like say, for example, product goes to product.price is larger than 49.95, instead of generating IL code, the compiler generates a data structure that represents that entire piece of code as an abstract syntax tree. That now a library at runtime can look at, cross-compile, for example, into T-SQL or any query language, and send it off to a database. The syntax looks exactly the same, and in fact there is some fancy name from the literature for the property of a lambda expression being assignable to a delegate and an expression tree. It's called homo-iconicity. Homo means the same, iconicity means the same shape. So basically using the same syntax, you can either go to an expression tree or a piece of executable code. So this is the whole menu of the C# 3.0 feature set. It's a pretty big menu. So we have lambda expressions and expression trees, which is this little syntax with an arrow where you can define a little function that says, given an A and a B, I return A and B, A plus B. So that's a very concise way to actually declare a little function. You have a feature called extension methods that I showed you before. So for example, if you're not pleased with the system.string type in the BCL, you can actually say, well, that damn system.string class, I wish it actually had a reverse method. And oh my god, they sealed the type, so I can't create like a superstring method or a superstring type. So instead of doing that, you can now say, I'm just going to create an extension method called reverse on system.string that does everything from the outside. We also have local variable type inference. We have things called object and collection initializers. So you can actually initialize an object by calling a constructor and in the same go, in between curly braces, assign all the properties that you want to assign. You can also create a new list of int, for example, by doing curly brace 2, 3, 5, 7, instead of calling 5 add methods consecutively. So you can do much conciser pieces of code. We have anonymous types query expressions, and one of those little features that was added is auto-implemented properties. If you want to define a property that's just a smart field, meaning that you don't really have a public field, but you still have a get and a set method between it for good measures, because that actually allows you to do more versioning. You can actually now say, I do an auto-implemented property, int age get and set, and the compiler generates some backing field for you. So you don't have to create a private field with a get and a set method that assigns or returns that value. But it's still a property, so you can always go back and expand the get and the set method using your own logic. So it's just a shorthand syntax if you don't want to type that private field in case it's trivial. So let's take a look at link syntax in C# 3.0 and some of the capabilities it has. So the example I have here, don't really need this thing, is first of all what I did is I created something called a data context. A data context is, in this case, a link to SQL data context where I basically go to a SQL database and I say from Server Explorer, I want to do an OR mapping for certain tables. So for the Northwind database, say that I want to query over products, and maybe I also want to query over categories. You can basically drag and drop those things on there, and it generates, all the code for the object relational mapping for you. Now, the thing that happens is that what we generate as well is something called the data context. That's basically the entry point to the database where you can get access to, in this case, the products table and the category table. So using that generated type, which is called Northwind data context in my case, I can basically dot into context.categories, I can dot into context.products, all of those things. Now, instead of just sending T-SQL queries to that in some magic string, which doesn't have type checking and whatnot, I can write queries using link syntax. So I can write something like from P in context.products, where the unit price is larger than $49.95, select both the product name and the unit price, and I'm going to create an anonymous type that basically aliases product name with something more meaningful to me, which is name, and unit price, well, I don't care about the unit part, I will just name that thing price. And so as soon as I do that, and I've enabled some logging here, when I execute this thing, that link syntax, through the magic of expression trees and rewriters at runtime, gets turned into a T-SQL statement that's sent to the database engine. And you actually see that the T-SQL statement is even parameterized, which means that if you have multiple queries that filter on the price, and the price is always different, the database has a chance to basically create a query plan for everything that filters on price where the price is yet unknown. So we parameterize by default. So that's what you get here, generated code, and actually you can write very big queries and it generates the SQL code for you. One of the nice things is, though, that you can use exactly the same syntax both for SQL, for XML, for SharePoint, for Active Directory, for Amazon, whatever. Everything that implements a query provider, you can talk to using link. So for example, I can also talk to getProducts, which is an in-memory collection. So getProducts basically just returns a list of product, which contains product name chai and unit price 18 and so on, exactly the same as in my online database. I no longer need the data context in this case. When I execute this code, well, exactly the same query now executes locally against my in-memory piece of code, or data better. So as you can see, Link is really this unifying query language on top of different domains, including in-memory, hierarchical databases, relational databases, web services, those kind of things. So that's what we have with language integrated query. So we already ended up in 2010. We did quite a few things, in 3.0 and 4.0. We again had one theme of unification. So that's something you see quite commonly in the C# language design is we take a look at the problems that people have and we say like, almost 90% of people are doing querying of some sort, and they need to learn 5 different languages to be successful. Let's unify that. Well, we came to the conclusion there is exactly the same kind of mismatch in the field of dynamic typing and dynamic programming. A lot of people need to interoperate with COM, and COM has some dynamic characteristics to it, for example. Some people need to interop with the JavaScript DOM through Silverlight. Well, why is it that all of a sudden when you want to write code that goes to a dynamically typed language behind the scenes, your code doesn't look like C# anymore? You need to do a lot of plumbing yourself to make things happen. So in .NET 4, we actually decided to do something about dynamic programming, allowing languages like C# and VB to reach out to dynamically typed languages at the bottom. And so we introduced this thing called the dynamic language runtime, which is an optimized runtime for dynamic lookup of methods and all those kind of things. It exists out of expression trees, which are the link expression trees from 3.0 taken all the way to 4.0 with support for statement trees. So we can actually represent code that has loops and those kind of things in it as well as data. We have dynamic dispatch, which is basically looking up methods based on their name and finding things that match given certain criteria. And you have call-side caching, which means that if you do dynamic calls, historically dynamic calls, for example, to reflection, are kind of slow. Because always you go to a lookup path to find the right method, and then you find the method, and then you do an invocation, and then you do some casting, and so on, and you come back to where you started. And then you want to do exactly the same call, and it takes a long time again to do the same thing. So with the DLR, we can actually do call-side caching, which means that when you call the same method over and over again, even if it's dynamic, we generate optimized IL code that's specialized for that call site. So the first time it goes a little slow because we still need to do the dynamic lookup, but then all the subsequent calls to that same dynamic method are blazingly fast because we really generated optimized IL code for that particular call. And so we can reach out to a lot of things, including Python and Ruby, which have been ported to the .NET runtime as well. So let's take a look. The issue is the following. Say that you have a static type called calculator, then you can just write the following piece of code. You can say, given a calculator of static type calculator, I can do .add, and I will see IntelliSense telling me there is an add method. I can pass in 10 and 20, I can compile. The compiler says it's all happy because I know there is an add method. And ultimately, the code just runs. Now assume that you want to talk to a calculator of which you do not know the type. Say that you got some library and they have a public method that says get calculator and it returns a system.object. And there is no interface around to cast the calculator to. You cannot cast it to an iCalculator because they didn't implement it. They just gave you a system.object. So you don't have any type info. How do you make the call? The answer is you use reflection. You say, oh, I get the type dynamically, and then I invoke a member in between strings the add method, because trust me, dear runtime, I know there is an add method on this object. And you might have found it out through Reflect or any other tool. But basically, you're communicating your intent now in little strings, and you need to pass a lot of crap around. Like, the binding flags, you need to bundle all the parameters in an object array. Lots of stuff is going on here. But what's even worse is that when you want to interoperate with something else that's dynamically typed, say, for example, some implementation of Python or a JavaScript engine, typically you end up with an API that's totally different. Like, I might have learned how to do it through reflection, and I'm now the ultimate master to do reflection-based dynamic calls. That doesn't help me to do calls to dynamic methods, for example, in JavaScript, because then I need to use something like script object, which has an invoke method, and it takes a different signature, like everything is kind of ugly. So in .NET 4, we say, if you do not have a static type, we don't want to make it very hard on you to call to that thing. You can't make it that there is no static type, like that's not your problem. You just want to make the calls, so we allow to do dynamic calls. That doesn't mean we do away with static typing, because we believe that static typing is still a very good feature from, a safety point of view. Like you compile your code and it says, I don't find an add method that takes in 10 and 20. I think that's useful, that you can get checking at compile time. But if you do not have static types, we don't want to make it hard on you to actually make those calls anyway. So now you can say dynamic calc equals get calculator for any of the fragments above, though I wouldn't recommend you to do it for the very first one, because in the first one you have a static type called calculator. But for the middle two fragments, you can now turn them into dynamic calc equals get calculator, and then you can do calc.add. You won't get IntelliSense because we do not know the type. You basically say, trust me, I know there is an add method, and then you pass in 10 and 20 and you assign it to an int. In fact, there are two dynamic things happening here, which is looking up the add method and casting the result back to an int. Those two things are dynamic facilities that are the result of writing this little line of code. So some other things we did in 4.0, and I will actually demo the dynamic typing to talk to Iron Python in just a moment. Some more C# features are the following. In fact, I would say C# 3.0 was all about data integration. C# 4 is all about code integration, meaning you want to talk to dynamic APIs, you want to talk to, for example, an Office API. We want to make it easier for you to go from C# to those other worlds. So one of the other features we did is we added support for optional and named parameters, which is something that's very common in component object model COM-based APIs. So we said to make it easier for you to call into, for example, the word automation APIs, which, for example, have methods that take up to 28 parameters, 27 of which are optional, we now support optional parameters. In the past, you needed to do something like in C# 2.0, you needed to do word.save, and then you need to pass in the first parameter, which is mandatory, and then comma null, comma null, comma null, comma null, all the way to 28. Now we say, well, you can omit those things because we support optional parameters. Now, the reason we didn't do optional and named parameters in C# 1.0 is simply because, well, if people create a new language and a new runtime, we want to have some new guidance. We say, optional parameters are really a bad, ugly mess. Like if you create an API with 28 parameters, that's not the way we want to do it, because we do support things like overloading. You can have an API that has one parameter, an overload with 2, an overload with 3. That's the way to do it, typically for those kind of APIs. So we didn't want to encourage people to have optional parameters from here to the wazoo. So we said, let's not do optional parameters, but then we found out in C# 4.0 there are still a lot of COM-based APIs around, like Office APIs. Well, we still want to make it easier for people to consume those APIs. And in the meantime, the BCL has shaped up and it uses overloads, for all the things where it makes sense. So we introduced optional and named parameters ultimately in 4.0. And so you can see a couple of things here. You can declare on a method for each parameter what the defaults are. Those need to be compile time constants, like null, 2, and 1024. To call a method, you pass in the mandatory parameters by position, and then you can pick and choose the optional parameters by name or also by position. So for example, I can say, I want to call foo.txt with a UTF-8 encoding with buffer size 4096, where I basically use the default for the detect encoding parameter. Now, why do we use a colon instead of an equal sign for optional parameter specification? The reason is backwards compatibility. Like, if you would do something like, open text file txt, foo.txt, UTF-8, comma, buffer size equals 4096, that code already worked in C# 1.0. It basically means find a local variable or a field called buffer size, assign 4096 to it, and use the result of the assignment as the third parameter to the method call. We don't want to be breaking changes with existing language support for 1.0. People might have written that crazy-looking code, we don't want to break them. So we had to choose for a colon syntax instead of an equal syntax in that particular space. If we would do it again, maybe we would say, well, assignments are no longer treatable as expressions. So you wouldn't be able to write the C# 1.0 code with the equal sign in the first place. But, it's always good to be backwards compatible. We also did some stuff for improved COM interop, which means we use, for example, dynamic typing. In a lot of cases, you need to pass ref modifiers. Don't care about it. You don't have to do it anymore with C# 4.0. And also the deployment of interop assemblies to, for example, Office APIs is no longer necessary because we have a feature called no primary interop assembly. Don't care too much about that. That's just some cleanup that has to do with language and runtime support. One more C# feature before I go into a demo here is generic co-and contravariance, and that's kind of a funny story. So here I have an example of C# code, and actually Java code, that would totally perfectly compile. You could say, get some array of apples, assign it to an apple array, and then I want to call some method called makeJuice that accepts the apple array as a fruit array. That's something that's totally fine to do. You can basically call that method. However, this thing is not type safe. You can actually violate the type safety features here of the runtime by, for example, in makeJuice saying, hey, I got a fruit array. In reality, it's an array of apples. The guy who called me knows that it's an array of apples because that's what he actually created in the first place. But let's insert a banana in the 0th element of the array. So the thing that's now happening is that somebody upstairs, in the call site, could look at the variable called apples, index into apples 0, think it's an apple, but in reality there's a banana sitting there. And on an apple, you might call the peel method, and the peel method on an apple is not compatible with the peel method on a banana. It's a totally different process. So you do have some problem there. You have a type safety issue. So why did we enable this in the first place? The reason is that we actually wanted to have true cross-language interoperability. And unfortunately, some languages, which you can already infer from the context here, did ship with broken array covariance for a long, long time. And we wanted to have those languages on the .NET platform as well. So we actually consciously decided to break array variants, but insert runtime checks, so we actually get an exception here. We don't blow up the virtual engine, the virtual machine, which some other languages at that point actually did. Instead of blowing up the virtual machine, we throw an exception at runtime that this is not safe to do, but we are compatible with languages that believe it's safe to do. Now, okay, that's a little unfortunate that we had to make the decision. However, we can do better now in C# 4.0. And the reason is as follows. The true problem that this piece of code is fundamentally unsafe is that an array is both readable and writable. If I couldn't write a banana into a fruit array to begin with, I wouldn't violate the type safety. So if it's a read-only collection, we can make it safe. So that's what we do in C# 4.0. We support something called generic definition side co-and contravariance. That's the full name of the feature. What that allows you to do is, for example, say, I want to get apples, and they come out as an I enumerable of apple. Now, an IEnumerable is something you can only get apples out of. You can't insert apples into it, because there's no method that accepts an apple. It's only able to pull things out of the collection. So now I can safely pass that to the makeJuice method that actually takes in an IEnumerable of fruit. That basically is just going to smash the whole thing together and produce fruit or juice. Now, this is safe to do because I pass to the makeJuice method something in which they cannot insert something of a different type. So that's actually what co- and contravariance actually buys us. So basically, the idea is that code that didn't work before now starts to work automatically in C# 4.0. So that's a good thing. So let's take a look at dynamic typing really briefly, and then I want to show a little sneak peek of the future of C# as well. So here I have some dynamic interop code. I have a Python file with syntax highlighting, because you can install actually IronPython for Visual Studio nowadays as well. So we recognize the Python language. We can do the same with Ruby. And I have some calculator type here that has an instance method. That's why you have to use this self keyword here. The main difference between Python and Ruby is that in one you need to specify self and the other one you don't. And ultimately we return a plus b. So that's what's going on here. I have a dynamic type. I really have getCalc. When I call getCalc, I get an object, and I don't know the static type. That's basically what a property is of the Python language. So assume that you just downloaded a huge library in Python, and now you want to say, I want to call this thing from C#. How can you do it today? Well, you can say this. I want to get for the script file, I want to load up the script. You need to do like 3 lines of interop code here, where you say create a Python engine, create some scope in which the script will execute, load the script from a file and execute it in the scope, and then I will return the scope using the dynamic type. This is not a design flaw that we can have static methods that return dynamic. It just looks a little funny. So now I have something that returns a dynamically typed object on which I can do whatever I want to do. So for example, if I do get script for calc.py and do calc, I can dot into whatever. I can call the whatever method and it will blow up at runtime because the C# compiler doesn't know what's behind the scenes. But still, I can write it without having to do something like dot invoke with 17 flags, and then I need to specify here what I want to do. I can just dot into it. The code looks exactly the same as statically typed code. And so now I can do something like calc of add 1 and 2, but because it's a dynamically typed language, I can give it any 2 things that can be added together. Because the dynamic language runtime knows about the addition operation built into the CLR, so it can find for any object whether it can add itself to something else. So I can, for example, add datetime.now with 1 day. I can also add together 2 vectors, which actually happen to be my own defined types. I have like a vector type sitting here defined in C# that has a plus operator for 2 vectors. You can actually do operator overloading in C# all the way till C# 1.0. So when I execute this piece of code, you actually see that I've already added 1 and 2 together today with 1 day giving me tomorrow. And now I'm hitting the operator plus for basically the dynamic call that's happening from C# here into the IronPython code that ultimately did return a plus b for 2 vectors. And the dynamic language runtime actually said, well, wait a second, the plus method for the vector is actually defined in C# again. So now you have true cross-language interoperability between dynamic types, static types, all sorts of languages. So life is good. So finally, 2 more minutes on the next version of C#. I'm not going to show a demo for this one, but the next theme is asynchronous programming. You can find a great keynote by Anders Heilsberg from PDC 2010 on Channel 9 that explains the entire feature. But again, it's one of those unification kind of features where we come to the conclusion that in order to do asynchronous programming today, for example, in Silverlight, Windows Phone 7, JavaScript, those platforms, you basically need to be asynchronous, meaning you can't do blocking calls to, for example, a web service, because that will freeze your UI thread, whatever. So you need to be asynchronous. However, writing asynchronous code happens to be a little tricky. So this is a blocking call, you shouldn't do that. Download data on the UI thread, bad idea. So you want to do download data async today, with C# all the way to 4.0 you would write this code, but all of a sudden your code starts to look a little funny. Now I need to do download data async, pass in all the parameters, and then the remainder of my code needs to be lifted into a callback. I need to create a new function that will get invoked when the data becomes available, sometime later in the future. So in order to do that, I need to pass in those lambda expressions, and I can't write imperative style code anymore. Can I put a try-catch around download data async? Not that much, because you're only catching the call to download data async and not, the exception that might happen in the callback. So your whole composition starts to break down, like you can't use the C# language features anymore. Now in .NET, next version of .NET, you will be able to do async calls by using the new await keyword. So you can say, please await a download data async, and all the rest of the code gets basically lifted into a lambda expression that will execute upon completion of the method call. And so now you can write linear code again with ifs and whiles and for loops and try catches and finallys, whatever you want to do. But it still looks exactly like synchronous code, only that it happens in a non-blocking fashion. You're not freezing the UI thread. So a very small feature with a huge amount of leverage is typically what we try to do in the C# language. Even further, we want to open up the compiler so that you can take a look at the expression trees that it generates, and you can basically generate code at runtime. That's something I can't demonstrate here yet. We're still noodling around with that and prototyping that, but that's something you will see post the next version of the language. So with that, I'm actually going to skip this demo, but there are plenty of demos online. I gave a session on this feature earlier this week. You will find the video on Channel 9. Anders Heilsberg actually had a great session on the feature as well at PDC 2010. So with that, I'm actually at the end. It was kind of a roller coaster ride through the history of C#. I hope you enjoyed it and got some inspiration out of it. If you have any questions, I will be around for 1 more hour, because then I need to go to the Netherlands to speak on some other crazy stuff as well. Thank you very much.